Let me begin with a word of prayer.
Where's class?
Attendance is like really low today in all my classes. You guys are no exception. So I will get my whistle if I need to. Don't make me get the whistle. All right. Heavenly Father, we thank you for this day. I thank you for these students and for your many blessings this day, and pray that you'd just bless this class, help us to understand the material together, and to enjoy your creation that you've made. Lord, in your name I pray. Amen. Top hat is 6613. 6613. There you go. 6613 is the top hat. And generically speaking, like, this is your chance to top hat. You email me later, top hat didn't work. I'm sorry about that, but this is when you get the top hat. Because, like, I don't know how many emails I've answered this semester about top hat, but I'm done with them. Because the thing is, I don't really take points off for attendance unless you miss a bunch of classes, right? So as long as you're usually top hatting, it really shouldn't work against you. Now, if you have a drawn-out battle with IT and you go every day to go fix your top hat, and for 3 weeks on end you can't get top hat to work in any of your classes, then you can come talk to me about it. But short of a situation like that, let's try to avoid manual adjustment of the top hat. Because unfortunately, I've heard that professors in other classes have like lackeys, like dedicated lackeys just to take care of top hat. I have no lackey. It's just me. So, I mean, I have children, but I guess if I paid them some money to take care of top hat emails, they probably would. But that probably violates any number of federal, like, you know, privacy laws and stuff like that. So, probably shouldn't. All right. So, enough about the top hat. So last time we started talking about graphs. Do you guys like graphs? Do you prefer graphs to financial math? Yeah. So like it's much harder to mess up these things on your calculator, right? It's much more forgiving in that regard. Like the financial math that we just got done doing was, goodness gracious, there's just so much calculator work in that. I had no appreciation for how much calculator there work until we were in the midst of it. But anyway, so that is done, and well, until the final, right? But so a graph is a collection of vertices and edges. Here's some examples. A complete graph means that every vertice is connected to every other vertice, right? So if you do the math on that, that means that if you have n vertices, every vertex has to have n minus 1 edges, because you have to connect to every other vertex except for the one that you have, right? So, for example, this is a complete graph with 3 vertices. Each vertex has degree 3 minus 1, which is 2, because you need 2 legs to connect to the other 2 vertices, right? Here's 4 vertices. Each vertex has degree 3, because you need 3 legs to connect to the remaining 3 if you've got 4, right? Here's a complete graph with 5 vertices. And I get tired of saying vertices, so if you don't mind, I'm going to also call them nodes. It's just easier to say the word nodes. People use the word node instead of vertices sometimes. Let me write that down. So if in doubt, node equals vertice. All right. Now, what else can I say here? So like if you look at this complete graph with 5 nodes, each one of these has 1, 2, 3, 4 edges coming out of it. See that? 1, 2, 3, 4 edges. And so if every node is connected to every other node, it's called a complete graph, all right? And again, the degree of the vertex is the number, degree of the node, the degree of the node also, you could say, is the number of edges that are attached at the vertex, all right? We're generally not looking at too many things with like, this is a loop. If you've got an edge that begins and ends at a vertex, that's called a loop. You can also have multiple edges. You know, those sometimes are ruled out for certain theorems we have. Let me go on. So last time we talked about the Eulerian. I can't say it today. Let me sip some coffee. Maybe that'll fix it. So a connected graph is Eulerian, or has an Euler circuit, if and only if every vertex of the graph is of even degree. So this star graph here, right? A circuit means the path goes all the way back to where it starts, right? It's a circuit, kind of like an electrical circuit, you know, completes from plus to minus, minus to plus. Same idea, circuit, closed path, if you will. And an Euler circuit is a path in the graph which ends where it begins and uses every edge just once. All right, so like here, if you can watch me, I'll trace it out here. So this each node here has degree 2. See, because there's 1, 2, 1, 2, 1, 2, 1, 2, 1, 2 edges going out of each node, right? So they all have degree 2, which means they're all even, right? And there's an Euler circuit. Here it is. We start at A, then we go to D, then we go to B, then we go to E, then we go to C, then we go back to A again. So there you go. That's the Euler circuit. And so I can express it in this, you know, sort of symbolic loop down here, and where I've labeled the nodes and gone. Any questions about this? The thing I got confused about last class is it seemed like we had a contradiction to this because we blew up the 2 bridges, and then one of you found a path that went through every bridge just once. But what wasn't emphasized during class was that it didn't begin and end at the same point, that other path. And so that wasn't a counterexample to this theorem, because it wasn't a circuit. The challenge 2 solution wasn't a circuit in the last class. We go on here. So there's also an Euler path theorem. The Euler path theorem says a connected graph contains an Euler path. What is an Euler path? Euler path is a path which uses every edge once. So we drop the condition that it has to begin and end at the same point, but it just goes and it traces out every edge in the graph just once. That's an Euler path. That would be what the solution was to that challenge 2 question was in the last lecture, which some of you may or may not have done. But if you look at the handout that I gave last time and look at challenge 2, that would illustrate an Euler path. Okay, so here's the theorem, though. It's a little bit more complicated, although not much more complicated. So a connected graph contains an Euler path if and only if the graph has 2 vertices of odd degree, all right, with all other vertices of even degree. So furthermore, the Euler path has to begin and end at those odd degree vertices, all right? So like an application of that might be like designing a path for people to walk through in an art gallery. Right? In an art gallery, you want people to visit each room just once, right? And you'd kind of like for them to, let's see here. I say draw edges illustrating possible paths from room to room, given the pictured doors. And so like this kind of illustrates a path that you might go through in order to do what here? I think it's to go through every door. Yeah, to walk through every doorway without going through any doorway twice. So it kind of forces you to, you know, go through each part of each room. So if you look at I adapted this from the textbook on page 239, and I tried to trace the textbook picture. I was trying to be lazy and just do exactly what the textbook has in it, but I failed because when I traced it, I accidentally deleted the door in your textbook right here. So in doing that, I've created a new example. All right, this is different than the one in your textbook because the one in your textbook has a door right here. All right. So we have this art gallery, and you can basically label each room as a node. And then I've drawn edges to illustrate how to get from room A to B to C to D to E to F, right? Like from room A, you can either get to room F or room B, right? But you can't get directly to C, D, or E, right? They're not connected directly. F connects to every other room, right? And like room D, you can only go to room C or room E in my art gallery here, right? Room C, on the other hand, connects directly to B, to D, and to F. Okay, so what we have is a graph, and the question of can you walk through each doorway without going through any twice, right? And go through all of the, cover all of the, well, going through all of the doorways is traveling every edge in the graph is what it means, right? So the question of can you do this is the question of does there exist an Euler path for this graph? So we can try the Euler path theorem. How do we do that? Well, look at make a, calculate the degree of each node. The degree of A is 2. See, because there's two edges coming out of A. See that? 2, right there. Let me see if I can zoom in a bit. Although, well, all right. I know. Come on. It just needs to last another half a semester, and then you can go to your home. True home is a dumpster, I think. Let's see here. All right. So I think as long as I talk to it that way, it knows it's on borrowed time, so it'll behave, So the degree of A is 2 because there's 2 edges, right? The degree of B, see B, where's B? Here. So you've got 1, 2, 3, 4. You have 4 edges coming out of B, right? The degree of C, 1, 2, 3. The degree of D is just 2. The degree of E, again, just 2. And the degree of F, 1, 2, 3, 4, 5. All right? So the Euler path theorem says that if we're going to find an Euler path, we have to begin and end at the odd degree nodes. All right? Which it means we have to either start or finish at either C or F. So we should make the entrance to the art gallery, let's say at C. And then you put the gift shop at F, right? You always exit through the gift shop, right? That's the rule. Is that true for art galleries too? Do art galleries have gift shops? Oh, okay. Is the whole art gallery the gift shop? Sometimes. I don't know. I'm not very artsy personally. Yep. Oh, theorem, yeah. Good question. That is my default abbreviation for theorem. Good question. So let me zoom back out here. So, come on. Come on. You can do it. All right. We made it. We made it. Okay. It's okay. So anyway, so here's a path you could take. Starting at C, watch this. We can go C to B. I do C to B, then to A, then to F, right? And then I take F. I go back to B again, and then I go back to F again. And then I think what I did next was I went to E, then I went to D, then I went to C, and then I went to F. And so if you keep track of that, I have gone through every single door in the art gallery by traveling that path. And I just did this by trial and error. Basically, I followed the advice of the theorem, which was to try to begin and end at the vertices of odd degree. And I look for a path where I'm always going through a new door, basically, right? And I also try to make sure I don't end up somehow like working myself into a corner. But the book does not give any kind of algorithm. It basically just says you can do it by trial and error. So I did it by trial and error, and I got it on the first time. I don't know if I just got lucky or what, but there it is. Now, in terms of like how I would test on this, I think it's much more likely that I give you like multiple choice paths, and I ask which one's an Euler path for a given picture. Because the thought of asking you to put in short answer a sequence of letters like this, and then to look at 100 of those and try to decide whether or not they're right or wrong. That seems very scary to me as a grader. Like, I want no part in that. Because if I step back away from this, all I see is which is hard to grade. But anyway. Weighted graphs. All right. This reminds me of Bed Bath & Beyond. You guys been to Bed Bath & Beyond? There's like a 25% sale right now. It's really exciting. Although I would point out it's really still 75% overpriced. You can get a pillow there for $80. They have pillows that are $80. Why? Like, do you guys have $80 pillows? Am I just missing out? Am I not like living the right way? I don't know. It's easy to understand why they're going out of business, but we did get a couple of really pretty baskets for $4.50. That was exciting. And I've got my eye on one of them. They're the foot things with the foot bath. Like when they get to 75%, I might come back. But this is Lynchburg, so it's going to take a while. I still remember the closing of Toys R Us across the street. It took forever. Eventually they got to actual sales, but I digress. So a weighted, anyway, the reason it makes me think of weighted graph is they have weighted blankets there my children were throwing to each other, and I was just waiting for them to like throw the blanket past the other child and into the overpriced pottery or whatever it was they were close to. And thankfully, it didn't break anything, though. So here we are. Although later the same day, my son broke his arm. He's okay, though. My descendants should not skateboard. That's what it boils down to. I tried it once for about 3 seconds, and then I was like lying up and looking at the sky, and then I realized I should not skateboard. So anyway, a weighted graph. What's a weighted graph? I think I'll define it eventually, but not yet. First of all, a Hamiltonian circuit is a little bit different. So the Euler circuit did what? It had to go through every edge just once, right? Hamiltonian circuit is a path that begins and ends at the same vertex and passes through each vertex of a graph exactly once. So the Eulerian circuits are to edges as Hamilton circuits are to nodes. All right? They're different ideas, but similar in flavor. And a graph which contains a Hamiltonian circuit is called Hamiltonian. The theorem about Hamiltonian circuits is a lot weirder. Here it is. This is Dirac's theorem. Consider a connected graph with at least 3 vertices and no multiple edges. Let n be the number of vertices in the graph. If every vertex has a degree at least n over 2, then the graph must be Hamiltonian. Okay, so what's n? N is the number of vertices, right? That's important. So how do you figure that out? You just count the number of dots. So for my example 3, you got yourself 1, 2, 3, 4, 5, 6 dots. So your n is 6. So n over 2 is 3, all right? To apply Dirac's theorem, we need each vertex to have degree at least 3. And so to count the degree of each vertex, you just count the number of edges coming out of each one. So like C has 1, 2, 3 lines coming out of it, which means the degree of C is 3. P up here, it's got 1, 2, 3 edges coming out of it, which means the degree of P is 3. B has got 1, 2, 3, 4 edges coming out of it. The degree of B is 4. R is got 1, 2, 3, 4, 5 edges coming out of it. The degree is 5. All right. U over here has got 3 edges. Its degree is 3. S has 1, 2, 3, 4 edges coming out of it. Its degree is 4. Lo and behold, every vertex has degree 3 or bigger, which means Dirac's theorem applies. The graph is Hamiltonian. So I stole this from your book. Your book has like the names of cities here, like R is Reno, S is I don't care, U is I don't remember the names of the cities. You can look in your textbook if you want to put names there. Yep.
Can you explain the multiple edges again?
Oh, that's just like in back here. Would be like that would be a multiple edge.
But why?
Because you've got two edges directly connecting the same nodes.
Oh, okay.
I think I do have examples with multiple edges coming up, so we'll return to that idea a little bit here in just a second. But now, if you look at this, the Hamiltonian circuit is this. So follow me here. P goes to B, goes to U, goes to S, goes to R, goes to C, goes to P. All right, and I'm going to ruin my my picture here and do it in color. All right, you ready? Here we go. We start at P, we go to U. Wait a minute, we start at P, we go to B. Right, there we go, B, and then U, and then S, and then R, and then C, and then P, right? So if you look at that, right, let me make them a little bit fatter. So this is the Hamiltonian circuit that I have made with green letters at the bottom there, yeah? And if you look at that, it's not an Euler circuit, right? Why? Why is this not an Euler circuit? What does an Euler circuit do? It crosses through each edge once, right? And starts and begins at the same point. It is a circuit, right? It does begin and end at the same point, but it's not an Euler circuit because look at these other edges. This edge is not covered, this edge is not covered, this one, this one, this one. None of those we traversed, right? Not an Euler circuit, but it is a Hamiltonian circuit because it has covered every node. P, B, U, S, R, C. All of them have been crossed, therefore it is a Hamiltonian circuit. Hamiltonian circuits don't have to go through every edge. And of course this one does not, right? So that's all there is to it. Fun fact, I thought this was interesting. You guys can disagree, but this Dirac is Gabriel A. Dirac. He was the stepson of Paul Dirac, which is interesting. Paul Dirac, together with Schrodinger, were the authors of quantum mechanics. I mean, there were about probably a half dozen people, probably more, probably a dozen people, really deeply involved in the formation of quantum mechanics. But certainly Dirac and Schrodinger were the two of the main instigators of quantum mechanics. And you know, quantum mechanics basically underlies most of the electronics we use today, and pretty much the technology we're using for the modern world. And of course, you know, other things like it gives chemists stuff to do, you know, things like that. But I thought that was interesting because he's not like, you know, he's not the biological son of Dirac, but he apparently is still, you know, I guess Dirac rubbed off on him a little bit. So, interesting. Okay, so a weighted graph, what's a weighted graph? A weighted graph is a graph with weights. Okay, it's like, okay, well, okay, what do you mean by that? A weighted graph is a graph where each edge is assigned a value. And the meaning of that value, it could be different things physically speaking. It could be that your nodes actually represent actual physical locations, right? And the weight is actually the distance between the node as traveled by the edge. Like that's one way you could assign weights, right? You could assign weights according to like the difference between values of something at the nodes. For example, you could have each node being like, for example, like a tank of water. right? And the water have pipes connecting it, which are the edges. And maybe maybe the weight of the edge is the difference in height between the water in one tank and the other. So the value on the edge could indicate, like the flow rate or something like that from one tank to another, something like that. I mean, you could imagine all kinds of different physical reasons and meanings for the edge values, but that we don't have to get into all that. It's just it's a weight. All right, it's a number we assign to the edge. Okay. Does that make sense? So here's one. I made it up. Example 4. I've got my A, B, C, D, E. I said they're bus stops, and I made the weights be the cost of the ride connecting the cities. All right, so like it's $2 to go from A to C, $3 to go from A to D, $4 to go from A to B. The D to E route is $2. The E to C route is $11. And look, you can take a direct route from E to B for $8. Okay. And I wanted to illustrate the greedy algorithm here, so I did that. What's the greedy algorithm say? The greedy algorithm is a way of tracing out a path in the graph according to the following rule. You start at some point, all right, and then you choose where you go according to which has the lowest weight. And also, you want to take the cheap route to a new place yet not traveled. All right, not yet traveled. So like, if I start at A, look at A. I got choices, $2, $3, $4, right? So I take the $2 route. $2 takes me to C. I look at C. I can't go back to A. I've already been there. I must go to a new place. So I go to E, $11. I get to E. I've got my choices of $2 or $8 at E, right? I choose the cheap route. I take $2, all right? That takes me to D. I need to go someplace I haven't been before. I've already been to A. I've already been to E. I must go to B. And that's $5. And at that point, I've gone to all of the cities. I've gone to A, C, E, D, and B. I've gone to all 5 cities. The greedy algorithm found me a path that goes through all the cities, right? So the greedy algorithm is a way of tracing out possible paths through a graph. Now, it doesn't always work. It doesn't always work. Like, here's my second choice. What if I employ the greedy algorithm starting at E? If I start at E, I do the greedy algorithm, it takes me to D. Then where do I go? Well, I've got my choices, $3 or $5, so I would take the $3 route, right? Where was I? $3 route at D takes me to A. And then I would take the cheap route, right? So I go to C. And then, oh man, then I have to go back where I started again, right? So at this point, I have violated the idea that I'm not going to any city twice. So the greedy algorithm doesn't always find you a path that goes through all possible nodes, all right? It might not. All right? So this is an introduction to what's known as the traveling salesman problem, right? If you're a traveling salesman, what do you want to do? Imagine you're a person who's spent the $300 to the expert who's taught you how to be a good businessman, right? This is what business people do, right? They spend money to other business people who have a business of selling business. That is unfortunate. Too many people get sucked into these things, but one of the things they're going to tell you is the more contacts you get, the better, right? As a salesperson, right? That's what you need. Contacts, sales pitches. And so if you want to, if you're a traveling salesman, you want to pitch your vacuum cleaner or whatever to everybody in the town, what do you want to do? You want to knock on every single door and be a nuisance, try to sell the vacuum cleaner to every single person, right? How do you do that? Well, you don't really want to visit the same house twice, do you? And you'd rather not revisit roads that you've already been on either. So you're kind of looking for this path that goes through each edge just once and visits all the nodes, if you think of all the houses and the roads which connect houses as a graph. This is the traveling salesman problem. It's unsolvable. All right, this is a famous unsolvable problem. And your book has this like pretty cool synopsis of a team of researchers who has run the numbers on, the traveling salesman problem in like, I think Britain it is. And it took them supercomputers for so long to figure out a path that goes to every single residence or whatever. There's no nice solution to this problem. If you could find a nice solution, you would probably get like a Nobel Prize in economics or something, all right? But if you have a complete graph, it becomes a reasonable problem because the complete graphs, the greedy algorithm succeeds. So for a complete graph, all of a sudden it becomes a reasonable homework problem or test question, because for the complete graph, you can start wherever you like and do the greedy algorithm, and you're going to find a path that goes through every node. You're going to find a Hamiltonian circuit. So every complete graph is Hamiltonian. By the greedy algorithm, we can, if you were a person who liked to prove things, you could prove it by the greedy algorithm. I'm not such a person in that sense, but anyway, here is a somewhat complicated looking graph, and I've employed the greedy algorithm to find the Hamiltonian circuit. So I started at F, all right? Let me ruin my graph by adding color, all right? So here we go. I started at F, and I'm going to pick, why do I pick 1? Because it's the cheapest route, right? 1 is the smallest weight. I got choices of 1, 15, 14, or 13. I pick 1 because it's the, so I start here. Why did I start at F? There's no reason. I just picked something, okay? So I go to F, I go to A, I get to A. The rule is I'm looking for a new node I haven't already been to, and I want to go the cheapest weight, lowest weight. So 2, 3, 4, 5. I'm going to go 2. That's the lowest one, right? Remember what I said last time? Ignore these crossings of the lines. They don't count. You can only connect at the dots, all right? Think of them like insulated wires, which don't really make connections. All right, so we get down to E. Now at E, I've got choices, 14, 12, 9, or 7. So I'm not sure exactly, but my theory is that my 5-year-old stole my whiteout yesterday. All I know is I had it in the morning for calculus, and then when I was looking for it later in the day, couldn't find it. And apparently I have left it in my office. Oh well. I was trying to, let me just scribble. This is not a thing. All right. Okay, so we got to E. Now, greedy algorithm. What are our choices? 14, 12, 9, or 7. So we pick 7. That's the smallest weight. That picks us up here to B. All right. Now, what do we have? Our choices are 15, 4, 11, 6. We choose 6 because that's the smallest weight. That brings us to C. At C, we have choices of 7, 8, 9, or 10. I think we will choose, we don't choose 3 because we've already been to A. So we need to go to the new node. Actually, once you get to C, you have to go to D because that's the one place we haven't been yet. And then finally, we go back to where we started, and I've got choices. I could either go, well, I guess I got to go 13. I mean, I don't know. But anyway, here it is. So there's the picture, what I just did. So that is the greedy algorithm. There is also something called the edge picking algorithm. I did not cover that. I haven't tested on it in the homework. You're not required to know the edge picking algorithm, okay?
Why did you go from D to B at the end since 11 is smaller than 13?
I need to go back where I started.
Oh.
That's the thing is, I got to loop back to get a circuit. I'm trying to find the Hamiltonian circuit is what that was my goal. And that brings us to our next topic. Woohoo! So, early enumeration systems. So I'll start with, so we're now in chapter 6. And so they discuss a number of different numbers. So this is it's a pretty hard segue right there, right? So from graphs to number systems, but such is life in here. And they talk about a couple different number systems in this chapter. Today I'm going to talk about the Egyptian one, let's call it the usual numbers, right? Now we're calling it Hindu Arabic numeral. If you don't mind, I am going to start calling these regular numbers, if that's okay with you guys, or base 10 numbers, because that's what they are. This is our usual notation for number, the Hindu Arabic numeral. And so the Egyptians, the ancient Egyptians, they had these hieroglyphics that they used for numbers. They had a stroke, was this. This is a heel bone. This is my attempt at drawing the scroll picture from the book. This is my attempt at drawing the lotus flower picture from the book. This is the hot dog from the book, pointing finger. This is the fish from the book, and this is astonished person from the book. They're respectively worth 1, 10, 100, 1,000, 10,000, 100,000, 1 million units. And the Egyptian number system is really simple. There's no subtraction, there's no ordering. It's just, you just put them out there and you add them up. So like, I don't have to put them in order. I can do, I did stroke, 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 heel bone, scroll, pointy finger, scroll, fish, fish, scroll again. So to convert, I got 3 of the ones. I've got 110 because I got that one heel bone. I've got 3 scrolls, 1, 2, 3. That gives me 3 times 100. I got 2 fishes, so I got 2 times 100,000. And I got, where did I get this 10,000 from? What was that? Oh, the pointy finger. Yeah, thank you. And so you add those together, you get 210,313. So there you go. Next time you're looking at, an Egyptian papyrus or something, as you traverse wherever you go in daily life, you can apply this to the real world as you, interact with Egyptian society, especially ancient Egyptian society. You see this written on the cave wall somewhere, you're like, oh, 210,313. So obviously very applicable. I don't trust this book. Like, I don't know. I'm not a scholar on early number systems, but like I would be totally unsurprised to find out that actual Egyptian numbers aren't based quite on these, and that this is just something they made up for this book. Like, I would be totally unsurprised by that, because at least when I was looking, so I was like taking a little bit of a look at the Rosetta Stone, which the book has pictures of. You know what the Rosetta Stone is? It's this, artifact we found, 150 years, 200 years ago, I forget. And it has Greek, I think Egyptian, right? And what is it? Something else I remember. It's got like 3 ancient languages. Sanskrit, is it? They said, oh, anyway, I can't remember. But the point is that those 3 different languages, it's the same thing in 3 different languages, but people already knew the ancient Greek, so they were able to translate to the other 2. It opened up all kinds of interpretation for ancient documents. This Rosetta Stone, very famous in the business of ancient linguistics. But if you look at, well, I don't know if it was that, but if you look at the pictures of the Egyptian hieroglyphics in the book, maybe you guys tell me, when you look at them, if you can see any of these things in those hieroglyphics, because I don't know if I saw them. So it just makes me wonder. Anyway, down here, I've got, what is that called? Stroke, stroke, heel bone, heel bone, heel bone, heel bone, lotus flower, fish. So what that means is 1 plus 1, 10 plus 10 plus 10 plus 10, plus 1,000 plus 100,000, you get 100,042. These are pretty simple. I think you guys aren't going to have trouble once you understand this is how to interpret it, right? Okay, so let's go on, because we're also talking about Roman numerals today, which are really annoying. So Roman numerals. So here's your base 10 number, 1, 5, 10, 50, 100, 50, 1,000. And correspondingly, Roman numerals I, V, X, L, C, D, and M. C is for century, from centum. You can think of it, centum as C, that gives us the word century. The M is from milli, which is giving us the word millennium, which we are more familiar with, right? Also, like millimeters. There's 1,000 millimeters in a meter, for example, right? Or there's 100 centimeters in a meter. Same thing. Anyway, so here are the rules. Let me not read them, because I can read them, but you just need to see examples, right? So we can all do 8, right? You got V, and then I. So we do 5 plus 3, which is 8. As long as the value of the Roman numerals are decreasing as you read it left to right, you just add. What gets complicated is when you've got something like this. See, here we go C and M. So C is smaller than M. So when you have C and then M, that denotes a subtraction. That denotes 1,000 minus 100. So this is actually code for 900. And because the X came to the left of the C, that means you're subtracting 10 from 100. All right? So the Roman numeral system has this weird convention of subtractions built into things written in particular orders. This is why elementary school math teachers everywhere rejoice if Roman numerals are removed from the curriculum, because you can imagine teaching this to children would not be easy. And then of course at the end we've just got 5 and then 2 and then 2. 5, 1, and 1, so that's 5 plus 2. So this is 997. Okay? I have more examples for you. 137 in, okay, here I did another Egyptian number example because I thought I just get sick of the Roman numerals. So here we go. To write 137 in Egyptian numbers, you need 100, because 100's a scroll, right? And the 30 you can get from 3 heel bones, and the 7 you can get from 7 strokes, all right? But is this unique? Not at all, right? In the Egyptian number system, you could also just, you could replace that scroll with like another 10 heel bones if you wanted. Or if you wanted to be really obnoxious, you could just write like 137 strokes. Yeah. So like the Egyptian number system is very forgiving. Like you can do a lot of different things. Roman numerals, on the other hand, are insistent that you break things down according to their rules, right? So here it goes. 539 is a Roman numeral. Let's break it down like this. It's 500 plus 3 tens plus 9, right? 539. So the 500 is D. 30 you can get from XXX. 9, we have to subtract 1 from 10 to get that. All right? So that's that. 648 is a Roman numeral. So I need a 500, I need 100, I'm awful close to 50, which means what I'm going to do is I'm going to take 10 away from 50, and then I have to add 8. Now, you almost want to take 50 and subtract 2 from it, right? But the thing is, you're not allowed to do that. You have to subtract like the next power of 10 down from what you're subtracting from. So I can only subtract 10 from 50. I can't subtract 1 from 50. All right. So here we go. So that's DC, that's the 600. XL gives me 40. And then this is 8. Here's 999 as a Roman numeral. So I take 1,000 minus 100, that gives me 900. Then this is plus 90, and then plus 9. So this right here, so you can kind of like, I guess I could add something here. Like this basically is let me write it this way. This is the CM. And this is essentially the XC. And this is essentially the IX. And then put them together like that. It's weird, right? Yeah. Let's see here. To get 1,362, we do 100 plus 300 plus 50 plus 10 plus 2. This one is easier, I think. Anytime you don't have to do the subtraction thing, I feel like it's easier, right? So I get 1,000, add 300, then I add 50, and then I add 10, and then I add 2, and there you go. That's 1362. So if you're watching a movie and at the end of it, the credits, it has MCCCLXII, they're lying, right? As far as I know, there were no movies in 1362. Yes? You guys ever try to figure out the date on the end of the movie by looking at this Roman numeral they stick at the end of it? Nobody else? Okay. As a child, I used to wait for the end of the credits because I wanted to see what the Roman numeral was to try to figure it out. Mostly because I couldn't figure out what these big Roman numerals were. Nobody never, like in school, we learned the small stuff, but we never quite had a clear explanation of the M's and the C's and stuff. So it was always a mystery to me. Anyway, so all of these examples, if you go back and you look at the rules, you probably can kind of make sense of them, right? So each numeral, the numerals are listed, so each has a larger value than the numeral to the right. You just add. Each of I, X, C, and M may be repeated up to 3 times. And the numerals V, L, and D are not allowed repeats. So like your 5, your 50, your 500, you just get one of those. You can't do more than one. And the only numerals that you can subtract from are you can only subtract a 1, a 10, or a 100, and those have to be subtracted from the next power of 10 up. Like you can only subtract the 1 from 10, you can only subtract the 10 from 100, you can only subtract the 100 from 1,000. Them's the rules. And it turns out that that's enough that you can add together and get everything else. So there you go, Roman numerals. Now, this is not quite in your textbook, but I thought I should add something. So what you got here, your textbook calls this right here, calls these, your textbook says that this is traditional Chinese. But the thing is, my wife has told me more than once that traditional Chinese is really, really complicated. So this is actually what I think a lot of, at least people from Hong Kong would call simplified Chinese, or simplified characters. Over here, these are the actual traditional Chinese characters for the numbers. So yeah, it's a little bit different. But the Chinese number system is actually very simple. It's also built on base 10. Here's some examples. So like 327, the way this works is this is 3, right? Under it you have this number. What's that? Well, it's not anywhere in here, is it? Because you have to look at my next page of notes. I should have probably put these first. But here's the tens, powers of 10. See if we can look at this. So like 100 is this thing, all right? So 300, and then this is 2. This plus is 10. So 300 plus 2 times 10 plus this. What's this? If I go down a little bit here, you can see the 7 right there, yeah? So this is, now I was asking my wife, did you ever write numbers like this in school? She's like, no, we did not. So like when my wife went to school in Hong Kong, they would just use regular numbers, base 10, Hindu, Arabic numbers for math. But you might find yourself writing like a sentence like this, left to right, for example, like, how we write on checks, like, $320.13 or something. Like that's the place you might, as a Chinese person, maybe write these kinds of symbols, maybe like left to write a number, something like that. But so this one's like 4,600, and then this is that's plus 0. That is 0, and then plus 7. I don't think there's any homework on these. I just thought it might be interesting, so, whatever. Because what? There's like a billion people that use this number system, right? So, actually, do they though? I think most people actually are using the base 10 numbers globally these days. Finally. So, we've reached the end of my prepared notes, so now we get to write. So what is a base 10 number? So base 10, something like let's just take an example, right? If I have 3,713, what does that equal? It is 3 times 10 to the third plus 7 times 10 squared plus 1 times 10 to the 1 plus 3 times 10 to the 0, right? I mean, I can write the 10 to the 0. I don't usually write the 10 to the 0, but my point is it's the same pattern. See, because 10 cubed is 100, 1,000 rather. 10 squared is 100. 10 to the 1 is 10. And 10 to the 0 is 1. So this is base 10. So when we use base 10, that's just going to be our, let's just say that that's our default in here. So for the other number systems, we're going to put like a sub something on it to indicate we're using another base. So let me give you like an example of that. If I had, 327, right? And that was base 8, what would that mean? This would mean we have 3 times 8 to the power, let's see here. So we do 8 to the power 2 plus 2 times 8 to the power 1 plus 7 times 8 to the 0. Do you guys mind if I don't write 8 to the 0, if I just write the last one like this? I think we can do that. This is what this means. Base 8, when you write 327 base 8, it's 3 times 8 squared plus 2 times 8 to the first plus 7. That's what that means. So if you wanted to say, what is that number base 10, we could work it out, right? So that would be what? 3 times 64 plus 2 times 8 plus 7. What is that? So here's the rule we're going to use in here, guys. If we don't have extra notation, it is assumed we're working base 10. All right? That seem fair? Because otherwise I'm going to write base 10 on every stupid thing that we write, and like that would get really annoying really fast. So 3 times 64. 3 times 64 plus 16 plus 7. That gives us 215. Now, if I was going to be symmetrical about this notation, I would say 215 equals 215 base 10. Okay? But we're not going to write that sub 10 because it's just assumed. Did you get it? Okay. Let's do another example. If I have 1, 0, 1, 1, base 2. So let me number these guys. Example 1. Example 2. Example 3. So here's base 2. So for base 2, your only choices are here are 0 or 1 for your digits. Okay? And in some sense, even using the word digits is a little bit wrong for other bases. Why is that? Where do digits come from? That's these, right? These are digits. You got 10 of them, most of us, right? So that's why base 10, the digits are based on 10. But we still use the word digits for like the numbers that go in the places for other number systems. So we're going to do that. For base 2, you only have digits of 0 and 1. So this here would be, and I think it might be, I've started my examples by going from highest power to lowest power. I think logically it's going to be easier, we'll make less mistakes if we go from lowest to highest, because that's a natural way to count up. Can we do that? Let's start with 1 plus 1 times 2 plus 0 times 2 to the squared plus 1 times 2 cubed. Let me just do some pointing. So this was that one. This was that one. This was that 0. And this gave me that 1. So what is it equal to? You got 1 plus 2 plus 0 plus 8. That number is 11. So the binary number 1011 is equal to 11. So these are called binary numbers, by the way, base 2 numbers. Binary numbers. Okay. Let me work out another example for you guys. Aw, man. Haha. Let's see here. That was page 11, wasn't it? So there are natural questions to ask here, right? Like, how do you get from, well, I mean, so far I've been looking at how to get from base whatever to base 10, but we can ask the other question around, like how do you convert a base 10 number to one of the other number systems, one of the other bases? Let's think about that for a minute, yeah? So example 4. Let's try to convert, let's say 575 to base 8. So when you're faced with this question, what you have to figure out is what's the largest power of that base that works into the thing. So for this problem, it's going to be helpful for us to calculate powers of 8 just as a reference, right? So I'll just draw it over here. We've got, 8 to the 0 is 1, obviously. 8 to the 1 is, well, 8. 8 squared is what? 64. What's 8 cubed? It is 512. Aha! So we can definitely get a 512 in that number, can't we? So what we should do is we should take 575 and subtract 512 from it, right? Because if I do that, that's going to be a good starting point. Let's see here. So 575 minus 512, we get 63. All right? Aw, man, 63. That's just shy of 8 squared. Whew. So we can do what? We can subtract 7 times 8 from that, right? So 7 times 8 is 56, right? 63 minus 56. So 56 is 7 times 8, right? So I can fit 7 times 8 into that. And that leaves me with what?